you guys have in your notes, but just go with me. Okay, so we talked about entropy, the variable S. Spontaneity means, is it going to happen, right, just on its own? Okay. Free energy, I don't know if you remember, but I said that's going to be actually the variable G. Okay, free energy. And this, I don't know, do you guys have this slide next? No? Okay, yeah, I did bring in, this is like just a review slide. Oh, it's moved down there. I think I have it twice. So we said something's going to spontaneously occur if it's like falling out of bed. It wants to disperse its matter, okay? And so actually we talked about this dispersion of matter is measured by your entropy term, okay? And here in a minute we're going to talk about the dispersion of energy is going to be measured by your enthalpy term. Oh, is that not cruel or what? So by golly, if you are both dispersing energy and dispersing matter, then it's just going to happen. It's going to be spontaneous. If instead you're making order, that's the opposite of dispersing matter. If you're like creating order, okay, and if you're taking in energy, then it's never going to be spontaneous. And actually, that's one of the things we're going to get to. So by definition, a spontaneous reaction or process, chemical reaction, is one that proceeds as written from left to right. So you got to write it down, you got to read it from left to right, and if it's spontaneous, it will go ahead and do that. And the reason it proceeds is because it's not at equilibrium. If it was at equilibrium, it would be going back and forth. So to achieve equilibrium, it needs to go from left to right. So a non-spontaneous reaction is one that, as you read it from left to right, somebody wrote it down, it's not going to happen spontaneous. It's not going to go there to get to equilibrium. So a non-spontaneous reaction, what we're going to see is that if you flip the darn thing around, then it will be spontaneous. You're like, dude, why didn't you just do that and call it spontaneous? So it is a non-spontaneous reaction is spontaneous if you take your hand and swipe the other way. Go from right back to left again. It is spontaneous that way, non-spontaneous from left to right, spontaneous from right back to left again. So those two slides taken together, if you have something that is non-spontaneous and you want to make it spontaneous, all you got to do is flip it around the reaction arrow. Seems like a little bit of semantics to me. But so one of the big things we need to do in this part is, how do you know the spontaneity? I love that word. How do you know the spontaneity of the reaction? Now is this where the slide is? Okay. So something is going to be spontaneous, have the tendency to just go, okay, if it is dispersing matter, and again, the entropy term enters into there, and if it is dispersing energy, and the enthalpy, or H term, enters into there. But those things can work against each other too, we're going to see. Okay, so we need to consider both of those. So the entropy change is the S, okay? And the change in energy is the H. So by golly, there's delta S and delta H. So our little equation to check for spontaneity, which is actually going to be your G thing, the check for spontaneity is going to have both of those terms in there. All right. So in Wednesday, we talked about entropy. So entropy, chaos, okay. If entropy is positive, so that's greater than 0, okay. We said if entropy is greater than 0, entropy is increasing, and we said that your system is becoming more disordered. More disordered. So this is like part of Wednesday's lecture. And if your change in entropy is negative, okay, we said actually there was order coming to the system. The entropy, if it's negative, change in entropy is negative, the entropy of the system has decreased, and the system is becoming more ordered. Just to kind of reiterate, I bet you guys are on board with this. This favors, I'll just kind of, I won't spell out spontaneity, I'll just S-P-O-N-T. This favors spontaneity, okay, and this disfavors spontaneity. Cool. So with regard to the change in energy, is energy being dispersed, or is energy being brought into the system? Dispersed by the system or brought into the system? We have talked about these before. We said that if the change in enthalpy, enthalpy, the change in enthalpy of a system is positive, or maybe I go this way, sorry. If the change in enthalpy of the system or reaction is negative, and I did this on purpose, if it's negative, we said it's exothermic. And to me, exothermic, doesn't that just seem like it's dispersing the energy? Okay? So that actually is going to favor spontaneity. That's what we've been talking about. This favors spontaneity. I like it when it makes sense. I think it makes sense. We call that exothermic, a negative change in enthalpy. And a positive change in enthalpy, we call that endothermic. A positive change in enthalpy, endothermic energy is put in, and that will disfavor spontaneity. Okay? So like I said, we're building up to this Gibbs free energy, this G term, which actually that is the thing that talks about your delta S and your delta H for the reaction. So the G thing, actually G is Gibbs free energy. It's also a state function, which means it's independent of path. And it's the value of Gibbs free energy that chemists and biologists and engineers, it's the value of Gibbs free energy for a reaction that people look at to see if the reaction is spontaneous or not, as written from left to right. My whole thing is, if it's not spontaneous, then just flip it around reaction arrow, okay? So if you calculate Gibbs free energy, you can identify spontaneity. Lots to write down for that one. Oh my gosh, hand cramp slide. All right, there you go. So that equation should be on the equation sheet I gave you for your final. Let's just double check. Aha, it is. Okay. So a value for Gibbs free energy of a reaction or a process can be calculated this way. So are you guys okay because about this? Remember, anytime you see that not, that actually means a number of things. but it means 25 degrees Celsius. That's a degrees Celsius. It also means 1 bar pressure. P is equal to 1 bar. And if it's aqueous solution, it means aqueous solutions are 1 molar. It means a lot. And sometimes that little knot right there will be important to kind of know that. All right. So here we go. This you'll also want to know. This is not on the equation sheet, but it actually, once you do a few of these problems, it will hopefully make sense to you. We've been talking about spontaneity, and if your Gibbs free energy for a reaction is negative, that's less than 0. If it's negative, okay, then your reaction is spontaneous as it's written, and it will go from left to right to reach equilibrium. But does that not make sense? Because we said, I don't mean to say that it doesn't make sense. I said it does make sense. Because just a minute ago, we said that exothermic reactions, that would be negative delta H, favor spontaneity. Dude, so that's already kind of getting the whole negative Gibbs free energy. Okay. We said a positive delta S, it's positive change in entropy, would also favor spontaneity. But notice it's times a -1 and the absolute temperature. By the way, T there is the absolute temperature, so that would be the Kelvin temperature if you ever need to do this on homework or a problem. Okay, so if your Gibbs free energy is negative, less than 0, the reaction is spontaneous as written. If your Gibbs free energy is positive, then the reaction is non-spontaneous from left to right, but spontaneous from right back to left again. Okay, so it's generally what we say non-spontaneous if it's positive. And if your Gibbs free energy is, did I throw you guys off? I'm sorry, I did that again. If your Gibbs free energy is equal to 0, okay, it's kind of a cool sort of deal. It's already arrived. There is no, it's going back and forth, but it actually is in equilibrium. There's no movement with regard to quantities, molar concentrations of reactants or products. It's at equilibrium. All right. So I'm going to kind of show you, to me, I think I'm going to show you why this is the case. But if you have something that's at equilibrium, the entropy, the change in entropy of the system is equal to the change in enthalpy divided by the absolute temperature. Okay, if you are, if your temperature isn't changing much, if you're kind of at constant temperature, and if you're at equilibrium or near equilibrium. So if we look at that at equilibrium condition, a few slides ago we said that the Gibbs free energy was equal to 0. So let's just go ahead and plug in Gibbs free energy equal to 0. If Gibbs free energy is equal to 0, then we can kind of move the terms, on either side of the equal sign, and we get the absolute temperature times the change in entropy is equal to the change in enthalpy. So that's kind of, and you go ahead and divide both sides by the absolute temperature, and you get the thing you saw a few slides ago. So that's at equilibrium, no movement. But when we're talking about reaction being spontaneous or non-spontaneous, we're looking for the movement. It's not at equilibrium. Okay. So there's 4 different possibilities with regard to plugging your enthalpy and your entropy, your delta H and your delta S. There's 4 possibilities of things that can be going on here. You can have a negative delta H, okay, and a positive delta S. See how that is? Negative delta H and a positive delta S. If that's the case, by the way, negative delta H, that would be exothermic. A positive delta S is creating disorder. So exothermic is the dispersion of energy. Disorder is the dispersion of matter. By golly, that thing ought to be spontaneous. And actually, there's no way it can go wrong. That sort of situation with a negative delta H and a positive delta S will always be spontaneous. They can't screw that one up mathematically, because your Gibbs free energy will always be negative. So that's scenario one. Scenario two looks like this, where we still have an exothermic reaction. Delta H is less than 0. But now we're creating order, because check out the delta S in parentheses there. Okay. Now we actually have a delta S that's negative. Delta S is negative, that means we're creating order. Okay, and that does not favor spontaneity. So it's not to say that Gibbs free energy won't be negative, that it won't be spontaneous reaction. Oh, darn it. Really? How did I do that? But if it is spontaneous, it's what we call enthalpy driven, because the entropy term was trying to work against it. Okay? So this down here at the bottom, it says, it's possible for you to have a negative Gibbs free energy, but that will only be the case if the magnitude, the absolute value of your enthalpy term, which is favoring spontaneity, right, because it's exothermic, is larger than the absolute value of the temperature times your spontaneity term, or your entropy term. Okay, so if it is indeed, if your Gibbs free energy is negative, if it's spontaneous as written, if you're successful, then we say it's actually driven by the enthalpy term, so it's enthalpy driven. So this one, not always will you have a negative Gibbs delta G. Okay, that's the second scenario. The third scenario then looks like this. Oh, sorry. The other thing about this is if you look at what needs to be the case, if the temperature gets too high, it's really not happening. So this actually is favored at low temperatures. Spontaneity will be more likely to happen. You'll have an enthalpy-driven reaction at low temperatures. Okay, so the third possibility is this one. Where now, if you look at the enthalpy term, delta H, it's positive. So if it's positive, that means it's endothermic, and that's the opposite of dispersing matter. So actually, it's our enthalpy term that's the problem here. So positive delta H means it's not going to favor spontaneity. But look at this scenario where we go ahead and say we also have a positive delta S. If your change in entropy is positive, you're creating disorder, and that does favor spontaneity. So now they're at odds, but the entropy term favors spontaneity, the enthalpy term does not. So again, it's possible to get a negative value for your delta G. But that's only going to happen when the absolute value of this term with the entropy, this term over here, this T delta S, this term with your entropy, if the absolute value of that is larger, because it's favoring spontaneity, than the absolute value of your enthalpy term. So in order for that to be the case, this is more likely to be spontaneous at higher temperatures. How many more slides do we have? I think we need to go
So the assignment sign? Wait a minute.
Okay, so how close are we to?
We
No,
have-
I just want to see.
Oh.
Mm-hmm. Okay, yeah, we aren't going to get to the assignment slide. That's okay. I can live with that. Can you?
Yes.
Okay, good. So the last scenario is this. This is the fourth of 4. So notice that the cards are kind of stacked against us, because here we have both an endothermic reaction, a positive delta H, and our delta S term is negative, which means it's becoming more ordered. So with that, there is no way you are ever going to get a negative delta G. So this will never be spontaneous, because this and this, they both disfavor spontaneity. Sad face. So here's a figure. It's not in your textbook, but it's kind of good. It summarizes what we were talking about. This, and actually, I think they're in order of when we did talk about them. So over here, we have the possibility of having an exothermic reaction that is creating a disorder. Okay, your Gibbs free energy is always going to be negative, spontaneous at all temperatures. I guess it's, yeah. And here, it was exothermic, but it was creating order. So it depends upon the temperature. And here, it was endothermic, but it was creating disorder. So this disfavors spontaneity, but that favors spontaneity. Okay. So, but this one down here that we ended with, okay, a positive delta H means it's endothermic. That's bad. And a negative delta S means it's creating order. That's bad. So that's why we said that actually those are always going to be non-spontaneous. Always. Okay. So there are 2 ways to calculate the change in Gibbs free energy of a reaction. This is one of them, and then this is the other one. And I don't know, does this kind of look like something you've seen before recently? I'll kind of ring some bells here. So we could, instead of this term, okay, we could substitute entropy, okay? We could also substitute enthalpy. So you can use this sort of kind of summation approach for any of those 3 things. It's like, hey, I've seen that before. Yes, you have. Let me look at your equation sheet for your test. Yep. See those top ones? That's what those are. So I think we're going to wait until Monday to do that example. That just means there's going to be more assigned Monday.
That's okay.
Okay.
It's a Monday.
Looks like you're okay with that. Monday before finals.